Okay, so we are going to look at practice problem number 5 for forces and motion analysis. And it reads, a rope connected to a 50-kilogram sled pulls it along a frictionless sheet of ice. The tension in the rope is 100 newtons purely horizontal. How far does the sled move in 3 seconds if it starts from rest? So the question is asking about how far. That's a descriptor of motion, and that tells us we should be looking at kinematics. So we're going to start with our kinematics process. All right, so what's our object? Well, our object that's moving, that we're looking at the motion, describing the motion of, is the sled. When does the motion start and when does the motion end? So initially it's when we begin that pull and the the sled starts to move. And it ends after 3 seconds. We're interested in knowing where we are after 3 seconds. So we draw our picture. There's our sled with our rope. And on that picture, of course, we have to define an origin. So there is our origin. Okay, so next step is our list. Initial and final position, initial and final velocity, acceleration, and time. So when it begins to pull, where's the object? Where's the sled starting? Well, it's at that 0. I've defined it at that 0. And we don't know where it ends. It starts from rest according to the problem. So we have 0 meters per second starting from rest. We don't know how fast it's going. We're not given the acceleration, but we know we're interested in 3 seconds. So what do we want to know about the problem? We want to know how far. Well, that is related to my final position. So if I look at the final position relationship that we've used for our kinematics process in the past, x final, don't know what it is, it stays in x final. X initial is 0 plus 0 times my time of 3 seconds plus 1/2, don't know my acceleration, I have my 3 seconds squared. So simplifying this relationship, I end up with x final is equal to 4.5 times the acceleration. So my acceleration becomes a variable of interest, and I'm not going to be able to get that through kinematics. But forces cause accelerations. The forces are what's causing this motion that I'm trying to describe, so forces may be related. So we'll do a force analysis because we need acceleration. Of course, that acceleration is in the horizontal direction. So we have the object of a sled. Let's start thinking about those interactions. What is the sled engaging with? And we know that it's interacting with the force of gravity. So the sled and the earth. And as we develop our interactions, we should develop our free body diagram. So, force of gravity is acting down. And just as a reminder, that's mass times g, which is also known as the weight. The sled is also interacting with the ground. It's squishing the ground down. So the ground is pushing back. We call that a normal force. And it's pushing in the vertical direction. The sled is pushing down on the ground, so the ground is pushing back up on the earth. Thinking about as we develop, making some predictions as we develop our free body diagram. I think about if there are any other forces acting on the sled in the vertical direction. There aren't. It's not changing its motion vertically, so I'm going to represent that in my free body diagram as those two arrows being equal. No net force in the vertical direction. Okay, what else is it interacting with? Well, the rope. So we have the force of the rope, which we call a tension. You can use either name for that. And that's between the sled and the rope. The rope's pulling to the right, so our rope force, our tension, is to the right. Those are the only interactions on the object. There's no friction in this case. It's a frictionless sheet of ice. And so we don't have anything opposing the motion, nothing else aiding the motion. Those are our interactions. So I'm interested in that horizontal acceleration, so I want to look at the motion that these interactions cause. which means I'm going to examine the forces in both the horizontal and vertical dimensions. So force number 1, my force of gravity, that is acting purely vertical. It's pointing down, so I have my force of gravity pointing down. Force number 2 is my tension. That's acting horizontally and it's acting to the right, so it's positive. And there's no force vertical. And force number 3 is purely vertical, and it's in the positive direction. So I've identified which forces cause motion in which directions or change motion in which directions. And then I can apply Newton's second law. And as a reminder, that tells me that the horizontal forces are equal to the mass times the horizontal acceleration, and the vertical forces are equal to the mass times the vertical acceleration. Now I need acceleration, and that's in the horizontal direction. So I'm going to look at that list first. Might need the vertical list, but we'll find out. So 0 plus t plus 0 gives me t, just a positive t, the tension, and that's going to equal the mass times the horizontal acceleration. I'm told that the rope has a tension of 100 newtons. I'm also told that the mass is 50 kilograms. So I can use that information to solve for my acceleration, and my horizontal acceleration is, of course, 2 meters per second squared. It's positive. As I've drawn the picture, net force is going to be positive, therefore the acceleration is also positive. I can take that acceleration, pop it back over here to find my final position. So I have 4.5 times my acceleration of 2, x final is equal to 9 meters. So again, recognizing that we have a kinematic situation that we want to analyze, what are we missing? Well, we're missing acceleration. Acceleration is caused by forces, so we can look at that force analysis, identifying the interactions, developing that free body diagram, worrying about what we need to worry about. We didn't even have to worry about the vertical this time. Acceleration is what's causing that motion change that I'm describing, and we see where we end up. Good job.